All right, so for today's lab, we are talking about conductivity, and this is solutions. So aqueous solutions are when you have a homogeneous mixture, and typically you have an ionic compound or a polar compound that can be dissolved. In water, and that is an aqueous solution. Okay, now some compounds will conduct electricity with a conductivity apparatus that has a light bulb that lights up, and I'll show you that in a second. Some solutions cannot conduct electricity, and some electricity a little bit in between. So those are called strong electrolytes, non-electrolytes, and weak electrolytes. So we'll be seeing examples of all those in videos. So you've got video experiments today, as well as understanding the molecular views. What's going on at the molecular level for an aqueous solution? That's something dissolved in water. So this is a review of what we've covered in Module 8 for the process of dissolving, when water does its thing, basically. So when we're talking about this conductivity apparatus, I've got two versions of it here. This is the video version. That's the actual one that you'll see. And then this is the cartoon version on the left here. So this is called the conductivity apparatus, and it's used to test if a solution will conduct electricity. So here's how it works. First of all, it's plugged in. Okay, so there's electricity supplied to the apparatus. And what we know about electricity is it has to flow through a closed circuit. So electricity or electrical flow needs a closed circuit. So this is a closed circuit, which is a circle, or basically one continuous line that connects. So let's follow that circuit from this plug. So there's this wire coming out one side of the plug and going into the light bulb. That's fine. So the light bulb will not light up unless this is a closed circuit. So this light bulb light only if you have a closed circuit. Right now it is an open circuit. And so continuing to follow along, this wire continues on here and it ends in this electrode. So there are two electrodes. Okay, we've seen two electrodes before. That was in the single replacement lab. The two electrodes in two different beakers, the beakers have to be connected with a string to close the circuit. So what will connect the two electrodes here, this blue side, and then this other electrode is the red side. Well, this red side continues on into the plugged in walled outlet and would be a closed circuit, except for it's open right here. So this connection between the two electrodes will only be closed if the solution being tested can conduct electricity. So if this solution has free flowing ions, so ions being positive and negative charges that flow from one electrode to the other electrode, okay, then the circuit will be closed. So if the circuit closes, then you can have the light bulb lights up. Okay, and then you will see varying degrees of that light bulb lighting up. A lot of light is called a strong electrolyte. A little bit of light is a weak electrolyte, and then no light is a non-electrolyte. So metals, we know, are good conductors. So this first, this diagram is the actual in this video, is the first actual conductivity is showing putting those two electrodes directly onto a metal plate. So this is a piece of metal right here. And we know that metals can conduct electricity. It's not an aqueous solution. It's just a piece of metal, and metals can conduct electricity like electricity being conducted through this wire. So wires are made out of metal. And so let's see what happens when we first test this apparatus. This light bulb you can see right now is not on, but when the two electrodes, okay, so let's turn this on here. I've got, pick this up, pause real quick. So there's two electrodes here. See, notice these two electrodes. Here's the one electrode, and then here's another electrode, and this light bulb is not lit. That's plugged in over here, and it's because it is not a closed circuit. Those two electrodes are not touching. So how they're going to close the circuit is through this metal plate, because metals can conduct electricity. So let's turn this back on. And you can see that's with the light bulb lighting up. So try that again. Oops, okay. So there's the light bulb lighting up. So let's get this back up. When you have the different possibilities of solutions, you have also different experimental results. So when you have these ions, which are charged particles, the positive and negative charged particles, when those ions are in the aqueous solution, the solution can conduct electricity. Okay, and so you will either have a strong electrolyte or a weak electrolyte. It's called an electrolyte. So you can have a lot of light, that's a strong electrolyte, or a little bit of light, that's a weak electrolyte. And if you think you've heard of an electrolyte, yes, you have, but I'll get to that in a second. So you have heard of an electrolyte before. So this is example A. For this conductivity, this is plugged in, and it would be a closed circuit from these two electrodes. So there are two electrodes, just like the other setup, but now they're dipped into this beaker of water. And you can see here that this is no light. So this sample is pure water. So it's H2O only. And so that means there are no ions. That's what pure water is. When you distill water, you basically boil off everything. The impurities get boiled off, any ions that are in there. And pure water should only have H2O, which is a polar compound. They are molecules. There are no positive or negative charges. There are partial positive and partial negative charges, but basically there is no closing of this electrodes. They're not being connected through ions because there aren't any in there. Okay, so you have no light. That's not conducting electricity, and so that's called a non-electrolyte. Now, this also is a light bulb where the two electrodes have been dipped into this beaker that has a solution in it. Now, this solution looks like water, but instead it's not just water. There's sugar dissolved in water. It's sugar water. Now, sugar is a polar compound. Sugar has the chemical name sucrose, and that is a polar compound. And polar compounds will dissolve in water. And with sugar, it looks like a white solid before you put it in water, and then after you put it in water, it disappears. So it's similar to table salt, table sugar, table salt. They look the same to start with, right? And then the same thing happens when you put them in water. They both will dissolve in water and disappear. But the effect of the sugar is that when you test it with a conductivity apparatus, you have no light. So that'd be one way to test, actually, if you had, put in a white solid in water and you want to know if it was sugar or salt to start with, you'd use this setup. So when there's no light, it means there's no electricity being conducted, that there's no closing of this gap here between those two electrodes. Okay, and so that's called a non-electrolyte when this doesn't light up. Now, this is the possibility when you do see the light, like the example where the electrodes are on the metal plate. You have this electrode and this electrode, two electrodes that are in this solution of salt water is dissolved in the water, and you have ions. So you have free flowing ions in the solution. And so you have the sodium ions that are positively charged, and you have the chloride ions that are negatively charged, and they're free flowing. There will be a distinction between the solid, where they're not free flowing, as a non-electrolyte as well. Okay, but this example of the salt water, you can see that this lights up. So there is a light. That means that this does conduct electricity. So this does close the gap where the ions allow these the flow of electricity through these electrodes and then through to close the circuit. So this would be the complete closed circuit through the wire, through the light, through the other wire, through the electrodes. And that is why this is an electrolyte and can conduct electricity. Okay, so you have to be able to connect those two electrodes by having ions in the solution that's being tested. So you have heard of an electrolyte sports drink before. So Gatorade, Powerade, these are electrolyte drinks because they have ions in there. So the ingredients, if you look at the ingredients of Gatorade, the top two ingredients are in fact water and sugar. And that's why Gatorade is watery and it tastes sweet. But why it's called an electrolyte is because it has also sodium chloride. So it has table salt in there as well. And so, whoops, go back here. If you don't know the story, or if you're not familiar with the story of Gatorade, that was the original electrolyte drink. And the reason why it is because it has sodium chloride. It has table salt. And so this came from the University of Florida. So the University of Florida football team, which was very big for a couple of decades, the reason why is they're sports scientists, and they had sports scientists back in the 50s and 60s. Let's give these athletes not just water, but water with a little bit of salt mixed in there. And because salt water doesn't taste very good, they threw some sugar in also. And so they made the first sports drink and which allowed their football team to do really well, better than all other football teams in the fourth quarter. And so that was the original discovery of when athletes sweat, they lose water and they lose salt. And so replacing that salt by giving them drinks that have sodium chloride was what allowed the University of Florida football team to dominate, and also led to them selling their secret, which is the Gatorade recipe. And not so secret because it's really just on the ingredient label: water, sugar, salt, and some color. So you can make your own Gatorade. That's what that means. If you actually do test the conductivity of the Gatorade, there's very little salt. So it's mostly just the water and sugar. How many of you guys knew the story of Gatorade before? I don't see any hands. That means it's new to you guys. So yes, named after the University of Florida Gators. That's their mascot. Okay, so let's talk about electrolytes. There are called strong electrolytes, and the electrolyte first is when you have the ionic compound dissolved in solution. Okay, so it's dissolved in water, and then it's called a solution, an aqueous solution, when you have the ionic compound dissolved in water. But what's different about these, which are called strong electrolytes, is strong electrolytes are completely ionized. And we'll compare them to weak electrolytes. So completely ionized means you have ions and only ions in the solution, and you have no or none of the compound. Okay, and so what that means, for example, the sodium chloride. So sodium chloride is dissolved in water. You see table salt, you dissolve it in water. Well, you don't actually have sodium chloride. Instead, what you have is the sodium ions, Na+, and the chloride ions, Cl-. And so that's instead of having this, you have this in the aqueous solution. And that's why the electrolyte is a strong electrolyte, because you have all ions. And those ions can conduct electricity. Okay, so when you have all ions, you have a lot of electricity conducted, you're going to have a lot of light. And so you have 3 types of strong electrolytes. There are strong acids. And remember, the definition of an acid is that an acid has hydrogen as the cation. So for the chemical name, acids always have acid in the name. So these 3, hydrochloric acid, nitric acid, and sulfuric acid, these are your strong acids. They all have acid in the name. Also, strong bases are strong electrolytes, and bases have hydroxide or can produce hydroxide. So bases, these 2 have hydroxide in the name, potassium hydroxide and calcium hydroxide. So these are your strong bases. And then another definition of a strong electrolyte is what's called a soluble salt. So these are ionic compounds that are soluble using solubility rules. Remember those solubility rules? They're not going to go away. We're still going to see them. But the solubility rules that say, for instance, nitrates are soluble. Okay, so these are called soluble salts, but these are basically just ionic compounds. So sodium chloride, potassium carbonate, copper 2 sulfate. They are ionic compounds, and you can check their solubility using those solubility rules 1 through 6. So what you have for these is the chemical formulas of the compounds. But remember, what I just said is, well, you don't actually have the ionic compound. Instead, and let's draw what you have for each of these, you don't have HCl. What you have instead, because it's completely ionized, is you have the ions. So the ions are broken apart, H+, that's aqueous, and Cl-. So having those ions are what are in the solution that is your beaker. Okay, and you can't see, it looks like water. All of these solutions look like water, but these ions are dissolved in there and they're too small to see. So for nitric acid, when you have a polyatomic ion, you first want to put parentheses around it before you split it apart into the ions. So this is parentheses around NO3, which is the nitrate ion. And you don't have HNO3. What you have instead in the solution is H+ ions, and then not broken apart into separate atoms. You have the polyatomic ion NO3-. Remember, that is called the nitrate ion. So you're still going to need those polyatomic ions lists, so have that handy. So that doesn't break apart into separate atoms. It is stuck together. That's the definition of the polyatomic ion. For sulfuric acid, that's the next one, H2SO4. This will break apart into the ions, but before breaking apart into the ions, first put a parentheses around the polyatomic, so SO4. And then when this breaks apart, what it means is you don't have the ionic compound. Instead, you have H+, that's aqueous. And then in parentheses, you have SO4-, that's aqueous. Now, one thing to remember is this in subscripts. So when you have a subscript that is outside of the parentheses, so any subscripts in your chemical formula become 2 things. They become a coefficient for one ion, and also a charge value for the other ion. So you have 2 ions in the ionic compound. And this sulfuric acid, back up to here, the sulfuric acid has a subscript 2. So I circle that in green. That subscript 2 is not inside of the parentheses. So because it's not inside of the parentheses, it's one of these subscripts that part of the chemical formula is going to be indicating that there are 2. That's the coefficient 2 in front of the hydrogen ion. Okay, and that subscript 2 also becomes a charge value, -2 on this ion which is the correct formula and charge for the sulfate ion. So that's SO4 with a -2 charge. And so notice that that subscript 4 didn't go anywhere. Neither did that subscript 3. Why don't those go anywhere? Because they're inside of the parentheses. Remember, the polyatomic ion, you keep it in parentheses, nothing goes in and nothing goes out. Okay, so what you have are these ions, and those are your acids. Now let's take a look at these bases. So the bases have hydroxide in them, and hydroxide is a polyatomic ion. So before splitting apart the chemical formula KOH, I'm going to add parentheses around OH. And so this is not KOH, but instead you have K with a positive charge, that's aqueous. And this is OH in parentheses with a negative charge, that's also aqueous. And that's your hydroxide ion. So for the next one, there's already a parentheses around CaOH2. But what you can see here is a 2 that's outside of the parentheses. So that's a subscript in the chemical formula. And so what that means is when this splits apart, that subscript goes 2 places. And from the crossover rule, it originally came from the calcium. It crossed over and down. So when you're forming the ions or trying to figure out the ions, you cross it over and up. That's the reverse of the crossover rule. And so the OH that's already in parentheses, didn't need to add it. That's the negative charge, and that's aqueous. So that 2 crossed over and up and became the charge value on the calcium. And it also is a coefficient. That 2 subscript means that there's 2 of those OH ions, the 2 of the hydroxides. So when it follows just the, right here, let me erase that. That 2 means that there's 2 of what was immediately in front of it. Okay, and so crossing out all of these, you don't have any of those ionic compounds, you only have the ions. Okay, so for these salts, these are ionic compounds, and sodium chloride we've already looked at a few times. Sodium chloride, you don't have NaCl, you have Na plus and Cl minus, and both of those are the aqueous ions. For this next one, potassium carbonate, before splitting it apart, I recognize that CO3 is a polyatomic ion. So put parentheses around it. And then when this splits apart, it splits apart into K plus AQ and CO3 that gets a minus. And those are both aqueous ions. Also notice that outside of the parentheses, there's a 2. So the subscript 2 in the chemical formula becomes both a coefficient. It's a 2 in front of the potassium. So there's 2 of those. And it also becomes the charge value, the -2 charge on that, that this is the, you recognize hopefully as the carbonate ion, CO3 -2 charge. We've seen that before, right? And so this is copper 2 sulfate. So remember that Roman number 2. So remember the Roman number 2, or this Roman number is the charge value on the metal ion. So that's when you can have a metal with more than one charge. So copper Roman number 2 in the chemical name means you're talking about copper +2 or copper 2 plus. Okay, so let's try to remember that when we break this apart. I first want to put a parentheses around SO4 because that's a polyatomic ion. So when this breaks apart, you're going to have Cu plus, and that's aqueous, and then also SO4 minus, and that's also aqueous. So there are no subscript. There's no 2 or anything that I can circle and bring up and make as a coefficient. However, remember that this copper 2 in the name means that it's a copper +2 ion. Okay, so that means I need to multiply both of those ions by 2 to have the correct copper 2 ion. So from the name, it says copper 2 sulfate. So this chemical formula, I need this to be not just copper +1, I need it to be copper +2. So I'm going to multiply that 2, so it's copper +2. And I don't get to do it to just one ion. It has to be done to both ions in the compound. So that's also a -2 charge on the sulfate, which is good because that's the correct chemical formula for sulfate. Sulfate is not just SO4 minus, but it is SO4 2 minus. Okay. And so what happened is that basically writing the chemical formula, that's when you cross the twos over and down, they reduced. Okay, so this is the +2 ion and the -2 ion. And that's what you have in solution. You don't have the ionic compound, but what you have are those ions. And that's what makes all of these compounds strong electrolytes. When you have only ions in the solution, all of those ions will conduct electricity and you'll have a lot of light. Okay, let's take a look at the next slide. All right, so what you have at the molecular level is when you have the ionic compound dissolves in water, and we've seen this before. This is the ionic solid is NaCl. So that's a solid, and that's the purple and the green ions. And there's millions of these ions all strongly attracted together. This is the ionic bond is a very strong attraction of positive to negative, and not just one and one, but millions of those. And when you have all of those millions of ions, you can see those millions of ions because collectively they're not small. But when the water molecules, so these are water molecules, when the water molecules start to come in here, they do the process of dissolving. And the process of dissolving is that these water molecules will come in one at a time and pull off these ions and surround each ion until you have an aqueous solution, until you have no more ions attracted together. So the way this happens is because those ions are the positive charge and negative charges, and the water molecule. So here's the water molecule is the oxygen and 2 hydrogens, and it has that overall V shape. So the water molecule has the negative end and the positive end. Or another way to draw this more simply is just this V, with the negative end is the pointed end and the positive end is the open end. Okay, and so the water molecules surround each ion, but not in a kind of, haphazard way. It is that the negative end, the pointed end, you can see here, is attracted to the positive ions. So those are all the pointed ends, are the alignment of how the water molecules are surrounding the sodium ion. Okay, so this is a positive ion, so it's the negative ends around that. Or for the chlorine, that's the negative ion. The way the water molecules surround this is the positive end of the water molecule. So the positive end, the open end, okay? And so it's not the pointed end, it's the open end, or you can draw it like this, the open end, or I can add a few more of these. The pointed end are on the positive and the open end are around each negative. And so instead of having, you don't actually have the entire compound. What you have are these ions in solution. And so that makes this a strong electrolyte. Okay, and so the strong electrolyte molecular view is you start off with an ionic solid. And then when you put this into water, the water will cause these ions to separate. And this is what the molecular view of the ionic compound, once dissolved, is like. That those water molecules, those water molecules surround each ion. So remember, it's the pointed end around the positives, okay, or the open end around the negatives. And so that prevents the ions from coming back together and forming the solid. And we can't see these ions. These ions, once dissolved, they're separated. And once they're separated, they're too small to see. So they disappear. And that's the process of being dissolved. They didn't disappear. They simply are too small to see at this point. And so when you have these are free flowing ions, free-flowing ions, these will conduct electricity. And that's why this is a strong electrolyte. So they'll conduct electricity with the conductivity apparatus. And so why these are ions that are separated instead of the ionic solid is because you can go ahead and surround each one of these ions with water molecules. Okay. So this is your strong electrolyte, and you'll see a lot of light. Now, at the molecular level, this process of dissolving can happen for the ionic compound or a polar compound. So your solid can be an ionic compound or a polar compound can dissolve in water. The liquid that does the dissolving is water molecules. And what you end up is with a solution where all of those, either the ions or the molecules, are separated. So this is the more active example of what water does when you put table salt in it. So here's the molecular view. Trying to get this video to work. Doesn't want to do this for me. Come on, video. Thought I had this fixed. Okay. Have to show you that on the lecture videos. Okay, so let's talk about the weak electrolytes. So weak electrolytes are still electrolytes. An electrolyte is still when you have the ionic compound dissolved in water. But the difference between this, which is different than the strong electrolyte, is when there's a weak electrolyte, they're only partially ionized, that there's a reverse reaction arrow. So this can be drawn as a two-headed arrow. We've seen both of these. You've seen both of these, or a reverse reaction arrow like that. So that's a backwards arrow. That's because these are not completely dissolved, or you still have the ionic compound present. That's different. That's different from the strong electrolyte. For the strong electrolyte, you had no ionic compound at all. You have all ions. That's what partially ionized means. You have some of those aqueous ions, but not all of those aqueous ions. You still also have the whole ionic compound. And so they're going to be weak electrolytes because you don't have enough ions compared to the strong electrolyte. So less ions means less electricity conducted, and less electricity means less light that you'll see. So you'll still have some dissolves. So these are all ionic compounds still. And so these are your weak acids. The weak acids are having acid in the name. That's these top three: the hydrofluoric acid, the carbonic acid, and the acetic acid. Those are all weak acids. They have acid in the name, or hydrogen is the cation. And then you also have weak bases. So weak bases still have hydroxide in the name. They still have hydroxide or produce hydroxide in water. And these are examples of weak bases. And then you have what are called slightly soluble salts. And these are, by the solubility rules, you'll find that these are insoluble. And so by the solubility rules, for instance, silver chloride. Okay, so these are your slightly soluble salts. Silver chloride is not soluble, it's insoluble. But because water can actually dissolve things so that you can have a little bit, some ions in the solution, you'll still have some ions. And that's the definition of a weak electrolyte, is having some ions. So partially, even if it's just very, 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 very small amount, that's still having some ions in there. And water can do that, even when it's called insoluble. Okay. And so it'll still be written as solid, like these both are solid instead of aqueous, but you'll still get some partial ionization. So here's how to indicate these. And the key is that you have this reverse reaction arrow. So you either have the double-headed or the two arrows, including the reverse reaction, that's this one going backwards. Okay. And so let's draw what you have for hydrofluoric acid. So hydrofluoric acid, you have the reverse reaction. So you have the ions are the same process where you break it apart into the ions, but the only difference is the arrow. Okay, so you have the hydrogen ions, you have the fluorine ions, but you also have this compound, the HF, and that's also different. I don't just get to cross off the ionic compound. That's still going to be present. For the carbonic acid, just like the strong electrolytes, you want to start by putting a parentheses around your polyatomic, because when this breaks apart, okay, so this is a reverse reaction arrow for any of these weak electrolytes. This breaks apart into the hydrogen ion, H+, and then the carbonate ion, this is in parentheses CO3 with a minus. And so this is the aqueous ion, that's the carbonate ion. We've seen that before. And the carbonate ion, this has a 2. So notice that 2 subscript. So the same thing is true, is when you have a subscript in the chemical formula, that subscript in the chemical formula becomes, in the ions, a charge value and also a coefficient. So it's this subscript 2 means that there's 2 of these hydrogens, and it crosses over and up to become the -2 charge on the carbonate ion. And so that is the correct chemical formula and charge on the polyatomic ions for carbonate. Okay, so for the next one, acetic acid, you first want to start by putting parentheses around the polyatomic, so around the C2H3O2. And so when this splits apart, this has the forward and reverse reaction arrow. So this is going to be H plus AQ, and then in parentheses, C2H3O2 minus AQ. And so notice everything, all of those subscripts, the 2, the 3, the 2 are all in the parentheses, so you don't have to change anything or do anything else. They stay exactly where they are. But for the next example, ammonium hydroxide, there are 2 polyatomics. There's NH4, so I want to put that in parentheses. And then there's also the hydroxide ion, so I also want to put that in parentheses, OH. So when this breaks apart, have your forward and your reverse arrow, and then put in parentheses the NH4, and that gets a positive charge, and that's aqueous. And then the OH also in parentheses, and that gets a negative charge, and that's also aqueous. So that's NH4 is the ammonium ion, and then that's your hydroxide ion. So for magnesium hydroxide, the next one, you already have hydroxide in parentheses, so don't need to add any parentheses. So when this breaks apart, it becomes Mg plus, that's aqueous, and then also OH minus, that's aqueous. So outside of the parentheses is that 2. So that 2 becomes a subscript and also a coefficient. It is crossing over and up to become the 2 charge on the magnesium. And that should make sense because magnesium is in family 2A, and it should always have a +2 charge, not just +1. There's also this subscript means that there's 2 of these, the hydroxides. Okay, so the subscript is indicating what right before it, how many of those there are when it breaks apart to the ions. So for these silver chloride and calcium carbonate, so remember they are insoluble, and that's why it has an S. But it also means you will have some amount of these ions. You'll have this whole compound mostly, but you'll also have a little bit of this ion coming off, which is Ag plus and Cl minus. There's no polyatomic in that one. But for this CaCO3, calcium carbonate, the carbonate ion, you want to put a parentheses around CO3. And then when this breaks apart, you have the reverse reaction arrow. This is going to be Ca plus AQ and CO3 in parentheses minus AQ. And so calcium is Ca. And this is in family 2A. And family 2A always is +2 ions. And so what do you do with the fact that this is only a plus charge there? There's no 2. The 3 is inside of the parentheses. So I need to do the same thing like I did in the last slide. I need to multiply 2 by each ion. So that's each ion charge value. So this is +2, Ca +2, and then the CO3 -2. And that's the correct chemical formula and charge for the carbonate ion. It's also the correct ion for the calcium. And so why that happened was because when writing the chemical formula CaCO3, you cross the numbers over and down and then reduce down. So in figuring out the ions, the numbers crossed over and up and you had to multiply back up. Okay, sound good? So here's the molecular view. When you have a weak electrolyte, you have this ionic solid to start with. So it looks like the strong electrolyte to start with, but this time when you put it into water, the water does not separate most of this. So you can keep this together as the ions. And that stays stuck together. And so you have some dissolved ions, but most of that ionic solid remains. And you can see that ionic solid, and that's why it's this precipitate, or it's a solid that just sits at the bottom of the beaker. And so you'd have some ion can come off, but this ion comes off in the same way. It would be surrounded by water with a positive ion. It's the negative, the pointed end of the water molecules is how those would be aligned. And you'd have just some dissolved ions. So that's what it means to be partially ionized. So partially ionized is only some ions. And so that means you're going to have only some conductivity. And so that's why it is a weak electrolyte. And you would see a low light. As opposed to a lot of light from the light bulb in the conductivity apparatus. Okay, but what happens when you have a non-electrolyte? So there's 3 possibilities. A non-electrolyte, you still have an aqueous solution. This is an example of a polar compound. Polar compounds will also dissolve in water. Not all polar compounds, but a lot of them. Okay, so polar compounds will also dissolve in water by the same way. So by the water molecules surrounding the polar molecules. And then the way the water molecules surround the polar molecules is that the alignment of the water molecules still has to be partial positive. So here's a water molecule with the partial negative end and the partial positive ends, or the open ends. So the water molecule still has to align, but it's not going to be as predictable as the ions. And that's because your polar compound has some parts that are partial negative. So here's this partial negative. And so there would be a water molecule that would be the partial positive there. Or this white could be a partial positive. And so there are polar bonds inside of the polar compound. So remember, a polar compound has polar bonds in the 3D molecule shape. And it's the distribution of the polar bonds over the 3D molecule shape, which leads to the molecule polarity. And so there's some partial positive. The upshot is there's partial positive and partial negative spots in the molecule. So they're portions, they're parts, they're the little sections in the molecule. And so here's the example of having one part of it being partial negative, and there's a water molecule that comes in. One part of it being partial positive, and there's a water molecule comes in. So depending on what the polarity is of the entire molecule, this will surround each polar compound, just not as predictable as the ions. And so here you have a polar molecule. These polar molecules are separated because they are surrounded when you put them into water. Okay, and so you have an aqueous solution. You won't see the solid anymore, but you have no ions. So there are no positive or negative because it is not an ionic compound to start with. So even though you have dissolved particles, you need to have ions to have electricity, to have electrical flow. So this will not conduct electricity because there are no ions in there. And so for that reason, it's called a non-electrolyte. So you will see no light. Okay, so that's one example, is when you have a polar compound that's dissolved. And sugar water is that example I showed you earlier in that slide. Another possibility of a non-electrolyte is when you have an ionic solid that doesn't have any water. So take your ionic solid and just put it into the beaker with no water. Okay, so this means you're just going to dump this in there and it'll still be these ions attracted together that have not been separated by water. It was a solid before you put it in the beaker, and it's still a solid after you put it in the beaker. So that's a solid ionic compound, and you have no dissolved ions. So you need free-flowing ions, or they are dissolved ions. That's a dissolved aqueous solution. And you need those to conduct electricity. If they are not free-flowing, if they are all still stuck together, this is not going to conduct electricity. And so these ions will not conduct electricity. Why not? Because they're all still stuck together. And you'll see an example of this. If they're still stuck together, they're not free-flowing. That's not going to conduct electricity, and so you see no light. And this is another example of a non-electrolyte. And then here's another possibility of a non-electrolyte if you just have water. So if you just have water, H2O in here, water molecules, they are that V shape. So drawing a bunch of those V shape. The water molecule, it has partial positive and partial negative, but not any full positive or full negative. And so remember, you need free-flowing ions to conduct electricity. And so if you don't have any ions, it's not going to conduct electricity. So that's going to be another example where you have no light for the conductivity apparatus, and that's another non-electrolyte. Okay, so let's take a look at, not that yet. Let's take a look at this. So on your lab report, it jumps right into the experimental data is part B. And on the, what you need though for part A is understanding what you're looking at. And so that's what this diagram in part A is about. So you don't have any experimental data to write down, but just understanding at the molecular level what the results are. So let's take a look at, actually I'm going to focus in on the bottom part here, is when you have the results. What you will see is a lot of light, some light, or no light. Okay, now whether you're talking about a lot of light or some light, those are both because of an electrolyte. Okay, so a lot of light is high conductivity. There's a lot of electricity being conducted, so you get a lot of light. Some light is some electricity being conducted, so that's low conductivity. And the definition of an electrolyte is when you have the aqueous solution that can conduct an electric current, and that's usually because you have free flowing ions. So that's a soluble ionic compound, or a strong acid, a weak acid. Any of those are in the range, and they're all electrolytes. So those are strong electrolytes and weak electrolytes. So your lots of conductivity is a strong electrolyte. A little bit, some light, is a weak electrolyte. Okay, compared to having no light. So when you have no light, that's called a non-electrolyte. That's because there's no electricity being conducted. And why is there no electricity being conducted? Well, the possibilities we looked at. Why does this not conduct an electric current? The possibilities we looked at, this is one of them. All of them, you have to have no ions, okay? And what are the possibilities for having no ions? You could have a polar compound that's dissolved in solution. You could also have a basically something that's not dissolved. That would be a solid. So a not dissolved or a solid ionic compound. So there was no water added to it, or you could only have water. That there's no ions in there because there's nothing else in there. So if you have only water molecules. So those are the possibilities, but this shows the possibility of the sugar. This is a polar compound that's dissolved in water. And so that is an aqueous solution, but you don't have electricity because there are no positive or negative ions. So looking at both of these are electrolytes at the molecular level. You either have a lot of ions or you have some ions. Now, why do you have a lot of ions? That would be your strong electrolyte. So these are your strong acids, your strong bases, and your soluble salts. And why? Because those are completely ionized. Okay, so that's what completely ionized means, is you only have ions. All right, so you only have those ions, remember, because each of those ions is surrounded by water molecules. So completely ionized. Compared to having a few ions, that's when this is partially ionized. And being partially ionized means that you have some ions. See, there's a lot less. And those are your weak acids, your weak bases, and your slightly soluble salts. And remember, the reason is that you have only some ions is because there's the reverse reaction. So that's partially ionized because of the reverse reaction arrow. Either it didn't break apart very well or it reformed the solid, and usually some of both. So that is all understanding when you see the light bulb light up a little bit, a lot, or none at all. And that is getting ready to understand what's going on for part B. So let's switch to here's the data, collecting the data for part B. And this will get to starting the lab report. Okay, so in your lab report, let's take a look at that real quick. You have, this jumps right into part B. And so the video is going to show you and a bunch of things going on. And you need to first understand what you're supposed to write in these boxes. Okay, so let's go to here. In these boxes, you have physical state, conductivity, electrolyte status, and ionization. These are all original samples, and then you're going to add water. So let me switch to, you can write this on your lab report, but I'm going to switch to my slide for this so that I can write a few things down. So what you have in part B, and this is also going to be similar for part C, is you have different samples, and you're going to want to pause video and make sure you record what you see. So when you're looking at the physical state means it's either a solid or a liquid or an aqueous solution. An aqueous solution means that it looks like liquid, but you know there's something dissolved in it. So that compound can either be an ionic compound or a polar compound that's dissolved in it. Okay, and then conductivity. So conductivity is high, low, or none. So you're either going to see a lot of light, a little bit of light, or no light. Okay, that was for part A, showed you what the meaning of conductivity was. Then in the video, they're going to add water. And so then at that point, you need to add the electrolyte status. So what's a strong electrolyte compared to a weak electrolyte or a non-electrolyte? That's all going back to that diagram in part A. And then the ionization. Is it at the molecular level completely ionized, partially ionized, or not ionized, and that there are no ions? That's what not ionized means. Okay, and so this is going to be similar to the boxes and what you need to write in part C, which is the second video. You need to start with the physical state. So look at the compound. So you need to pause and make sure you look at it. Is it a solid, liquid, or aqueous solution? And remember, aqueous solution looks like a liquid. And remember, liquid, there's very few liquids. The only real liquid that we work with most of the time is pure water. And so that's pure water that is H2O with that physical state L. But you have the same things for conductivity. You want to write that you have high, low, or none. So that's a lot of light, a little bit of light, or no light. You have the electrolyte status that goes along with it, strong electrolyte, weak electrolyte, or non-electrolyte. And then you have the ionization. It's either because it's completely ionized, partially ionized, or not ionized. So I'm going to drop the two videos in the chat, the two video links in the chat. But you have these video links on the lab report submission page. So that is going back to here. Okay, so here is the lab report. So you're going to want to fill in parts B and C. And this is the lab report submission page. There are, for parts B and C, one video for each. So I'm going to drop both of these in the chat and give you guys some time to questions. You have some complete ionic and net ionic equations to write on the last page of the lab report. So this is extending what you know about aqueous ionic compounds. So when you have a balanced equation, the balanced equation shows the chemical formulas, it shows coefficients to balance the atoms on both sides, and it also shows physical states. So in this balanced equation, this one right here, you have chemical formulas, you have the reactants on the left and the products are on the right, okay? And this is the reaction arrow. So reactants are on the left and products are on the right. You have chemical formulas, and then you have some coefficients. You also have some physical states. Those are the subscripts in parentheses, okay? So now remember that you can write what's called the complete balanced equation, you can write the complete ionic equation, and the complete ionic equation takes any aqueous compounds are split into ions. Just like we did in those two tables for the strong electrolytes and the weak electrolytes, you want to split these into the aqueous ions. So instead of writing, for instance, HBr, because this has an aqueous physical state, you want to write this as the ions, which are H+, that's aqueous, and then Br-, that's aqueous. And I also want to point out that this coefficient carries through to both ions. So both ions, when this breaks apart into the hydrogen ion and the bromide ion, that means that you have two of each of them. That's what the coefficient has to carry through when you break apart the compound into the ions. So the next compound is this BaOH2. And so we saw how to handle when you have a subscript. So remember, when you have a subscript in your chemical formula, so the subscript in the chemical formula has two fates. It becomes a coefficient and also a charge value. So you have two ions, and this 2 coefficient becomes the coefficient of this ion, which is the hydroxide ion. So that's already in parentheses, and when that broke apart, it's OH minus AQ. So that's the AQ physical state breaks apart into the ions. And so this is the hydroxide ion, and why it has the 2 coefficient is because it's the subscript. Then that 2 also becomes the charge value. Okay, so it doesn't become a coefficient for the other ion, it becomes a charge value. And this other ion is the barium positive ion, and it becomes +2. Notice that they both have the AQ physical state. So when you have the aqueous compound, it splits apart into ions also with the AQ physical state. So that's everything on the left side. On the right side, you also have a compound, BaBr2, that is aqueous. So when it has the AQ physical state, you want to split it apart into the ions. So this will break apart into Ba and Br. Because the chemical formula has a 2 subscript, so that 2 becomes the coefficient. It becomes a 2 in front of the bromide, the Br minus ion. And it also becomes a charge value, the +2 on the barium. Both of those, notice, are aqueous, still is the physical state. They break apart into the aqueous ions. Now, one thing that does not break apart is anything liquid. So liquid physical state, that's L, does not break apart. So it does not become any of those aqueous ions. So this 2H2O is copied exactly the same in the complete ionic equation. So the complete ionic equation, you just take anything that has the AQ physical state, this one, and this one, that breaks apart, but not anything that is not AQ, like a liquid or a solid or a gas. Okay. And so that takes us to the net ionic equation. Now, the net ionic equation is removing any spectator ions. So a spectator ion is the same on both sides. So that's both the reactant and product sides. And when I say same, it means exactly the same. You have to have the same chemical symbol. It has to have the same charge value. It has to have the same physical state, and it also has to have the same coefficient. It has to be exactly the same in order to cross them out. So what is exactly the same here? I can see that Ba +2 AQ, all of that is exactly the same as this one, Ba with the +2 charge and the aqueous physical state. If it's exactly the same in all those respects, then you can cross it out. Same thing with this Br minus. So the coefficient 2, the Br, the negative charge, and the AQ are exactly the same as this one on the other side. 2 Br minus AQ, you can cross it out. Now, these are not exactly the same. You have 2H plus AQ is not exactly the same as 2H2O liquid. And 2OH minus AQ is not exactly the same as H2O liquid. So the things that are not exactly the same carry through to the net ionic equation. So that basically gets carried down. 2H plus AQ is the same here. Write it in the net ionic. 2OH minus AQ, that becomes part of the net ionic equation. Then you have the reaction arrow, and then this 2H2O liquid gets carried down as part of the net ionic equation. Now, because you can divide both sides by the same common denominator, the 2 coefficient can all become 1s. This would be the simplified net ionic equation. So that's the net ionic equation. It's removing the spectator ions. Spectator ions in a reaction are like spectators at a sporting event. The spectators at a sporting event don't actually participate. You're watching a basketball game, you're not actually one of the basketball players. The spectator ions in a chemical reaction, they don't participate. They're not changed at all in the reaction. And so that's why they can get crossed out. So the net ionic equation shows what actually is going on. And so you have that for hopefully review and also to help you complete the lab report.